Welcome to this movie on classical mechanics. My name is Jos Thijssen and I teach the second year classical mechanics course at Delft University of Technology. And that course covers the Hamilton Lagrange formalism. And so in this little movie I would like to show how you can see that the action is stationary and how the action is defined in terms of a Lagrangian, starting from Dalembert's principle. I hope the movie will be instructive. We start using Dalembert's principle, and Dalembert's principle is given by this expression where p dot I is the time derivative of the momentum of particle I. We take the inner product with the so-called virtual displacement delta Ri, and the virtual displacement is an instantaneous displacement which is compatible with the constraints. And then on the right hand side I can put here the total force, but that's composed of two contributions. One is the applied force and the other one is the constrained force. And if we take the dot product with the virtual displacement and sum over I, then Dalembert's principle tells me that I can neglect the contribution of the constrained forces, and so we only have the applied forces here. And for these applied forces we make a very important assumption, which is that they are conservative, and that means that they can be written as minus the gradient of a potential depending on all the positions of the particles R1 up to Rn. And we will also use the notation that this is, can be written as minus dV dRi. Now we make an important step. So the Dalembert's principle says that this should hold, and in fact it should hold at any time. So although the virtual displacements are instantaneous, I can define them for any time, for at any instance in time. And so if we have the time axis here, I'm going to consider a virtual displacement for all times between t1, starting time, and the end time, which is t2. I can only draw one component, and that's why I have put the Ri vector here in quotation marks. Now let us assume that we have a particular path, which is the black path, and the black path is called Rai. It's path number A. It's a path followed by all the particles I running from 1 through to n, but I call that path A. And now let's suppose that we perturb that part a little bit and we get path B, which is the red path. But there is an important restriction on the red path. I assume that I start from the same position as in the A path, and I also end at the same position. And so if I define delta Ri now to be the difference between the B path and the A path, I can say that this delta Ri at t1 and at t2 should vanish. So now that I have two paths separated by virtual displacements for every time, for each time, I can in principle now calculate an integral over, I can take the integral over Dalembert's principle. So I just take Dalembert's principle defined for each time and I integrate over the time, so it runs from t1 to t2. The right hand side also runs from t1 to t2. I've put the sums before the integrals, but the sums in the integrals can be interchanged, so that's no problem. So we have an equality between a left hand side and the right hand side, and in the sequel I will first analyze the left hand side and then the right hand side. The first thing we note in the left hand side, there is a pi dot, and I can rewrite that pi dot as an mi dot ri dot dot. And so I put that now in the expression of the integral here. I leave the sum out for the time being. And now I want to rewrite that integral, and I want to do that using partial integration. Why would I like to do that? Well, I want to get rid of the double dot here, and to get rid of one time derivative I can use partial integration and it would move to the other side. So more specifically, I would get first an integrated term which looks as follows: Ri dot as a function of t dot delta Ri, and I have to evaluate that at t1 and at t2, and then I have minus the integral running from t1 to t2 mi Ri dot, and then one of the derivatives moves to the Ri. Now, we have previously assumed, we have required, that the delta Ri at the start time and at the end time should be 0. So if I evaluate the integrated term, then this term here, evaluated at t1 and at t2, both gives 0. And so this term can be crossed out. And so I'm left with this term. Now, in order to evaluate that term, it's useful to look at the kinetic energy. So the kinetic energy can be written as a sum over I mi over 2 Ri dot squared. So if we take the derivative of this with respect to one particular r dot j, then from this sum the derivative will pick out the term where I is equal to j, and I would get mj r dot j. And you see that's exactly this term, except that here is an I and there is a j, but that's not so essential. I see that I can write the integral t1 t2 of pi dot delta Ri. That was the starting point. That was a term which occurred in the left hand side. That is equal to minus an integral from t1 to t2 of dt dri dot, and then we have dot dri dot dt. And now I have changed two things. I have restored the sums over I, both on the left and right hand side, and I have specified that the integral is to be carried out over the path A. So P dot I is that of number A, path number A, and then also obviously the kinetic energy on the right hand side should be evaluated for path A. And now we analyze the right hand side, and we do that using a Taylor expansion. And the Taylor expansion tells me that if I have a path, and that depends on all the velocities r dot I, and I perturb that path a little bit, and then I look at the difference with the original path, then the Taylor expansion tells me that I can write the resulting expression as the derivative of t with respect to the Ri, and then taking the inner product with the delta Ri's, and I should sum over I. And in that case delta Ri should be the difference between two paths, and if you remember, we had indeed defined delta Ri to be the difference between path B and path A. And so this guy here, that is the same as r dot bi. So we can now write finally the left hand side of my equation as minus the integral from t1 to t2, and then we write t as a function of all the Ri. So this is not a single Ri, this is all the Ri's of path B, minus T, the kinetic energy for path A, and we integrate that over time. So that's my left hand side. So here we see again the right hand side, and we would like to analyze that too. And it turns out to be a bit easier than the left hand side, because I recognize in the term here, the sum over I dv dri delta Ri, a Taylor expansion, as you can see here. So if I compare a v for path B, which is very close to path A, I can do again my Taylor expansion. This is analogous, but now in a different order than what I did for the t before. And we see that I can write this as dv dri times delta Ri, where I would like to remind you that this is Rib minus Ria. That's my delta Ri. So I can immediately write up the result here. This gives me a minus integral from t1 to t2 of v Rib minus v Ria, and that integrated over time. And so if we scroll back a little bit, we see that the left hand side gives me the difference in the kinetic energy of path B and path A, and the right hand side gives me the difference in the potential energy between path B and A, and they are both integrated between T1 and T2. So let us now summarize. We have the integral from T1 to T2 of T, and I will now write this, use this shorthand notation. That's equal to the integral between T1 and T2 of VB minus VA. Just remove the minus sign on the left and the right hand side, integrated over dt. And so we can also state this as follows: the integral T1 T2, let's take all the terms with b to the left hand side, then we see this is TB minus VB integrated over T. That's T1 to T2, the integral of TA minus VA. So what does this result tell us? Let us assume that A is a mechanical path, so that it's a path which obeys the equation of motion of Newton, and therefore it obeys Dalembert's principle, which we have applied throughout. In that case, if we perturb that path a little bit to change it into B, then we see that this integral does not change, because it should be the same on the left and the right hand side. Of course, we have made approximations because we have used first order Taylor expansions at this instance, but also for the kinetic energy, so here. So to first order, we see that this integral does not change. If TA is a genuine mechanical path which satisfies Dalembert's principle, then a path B which is slightly distorted to first order will have the same value for this integral. And this integral is so important, and we will meet it so often that we give it a name. In fact, we also give the integrand a name. We call the integrand here LB. This guy we call LA. And L is the Lagrangian. And L is a function of the Ri. It's a function of the velocity, and there may be an explicit time dependence. So that's the integrand, and the integral of t1 to t2 of L integrated over t, that is called S. And for S we use the word action. So this is the action. And so we see that the action does not change to first order if it's evaluated for a mechanical path. So we can summarize our conclusion as follows. The mechanical path of a particle moving in a conservative potential field from a position r1 at time t1 to a position r2 at t2 is a stationary solution of the action, and that means that the linear variation of the action with respect to an allowed variation of the path around the mechanical path vanishes. That's a very important conclusion of this analysis. There's one very important remark to be made. So we assumed that the path A was a path which satisfied all the equations of motion, and that it was a correct path in agreement with constraints. In fact, path B was obtained by displacing path A via a virtual displacement, and a virtual displacement should be such that a new path also is in agreement with the constraints, and therefore all the paths that we are talking about are paths that satisfy all the constraints that were imposed on the system. So that concludes this movie on the Lagrangian that can be derived from Dalembert's principle. Now, the Lagrangian is a central concept. It's extremely important in analytical mechanics, and it turns out that it gives you the possibility to analyze quite complicated systems in a very easy way, and I hope to make a few additional movies where I will illustrate how that works. However, it is very important to know where the Lagrangian comes from. You can also take a different approach and start from the Lagrangian and the actions and require that the action is stationary, and then it's not difficult to derive that Newton's equations come from this. Personally, I think it's nicer to start from Newton's equation and then derive Lagrangian's principle. Thank you for your attention.